Hi everyone, welcome back to Causality with Boris, broadcast from Sobolev Spaces. In this video I talk about attributable proportions within causal inference framework. Attributable proportion for the population and for the exposed, no prevention assumption, and the probability necessity estimator are the three main topics in today's lesson. Now, I'm sure you will watch the video to the end if I tell you that you're going to learn how to correct the excess risk ratio widely used in epidemiology. There will be additional material prepared for this video. Click on the link in the description and it will be sent to your inbox. What if questions involve counterfactual reasoning? We see outcomes that occur in the study population and ask, what is the probability that the outcome would not have occurred in the absence of treatment? We wonder whether the outcome would have been different if treatment had been different. We looked at the probability that Y would change if X took a different value than it did. This kind of reasoning is common in public health. Consider all patients who died a few years after treatment for heart disease. The treatment might be medication, surgery, or angioplasty with stenting. Then we ask how many deaths could be avoided if they all received surgical treatment. That is, we would like to know what proportion of patients would have survived if they received surgical treatment. We think of the attributable proportion as the expected reduction in outcome if everyone gets effective treatment. We use counterfactual language. Some outcomes would not have occurred if the population had been treated differently. When concerned with harmful exposure, we find the proportion of cases that would not have occurred if the population had not been exposed. This proportion is what Pearl calls the probability of disablement. In his language, disablement means that the absence of exposure would have prevented outcome when we observe that the outcome has occurred. In this sense, attributable proportion estimates the probability that the observed cases would not have occurred if the population had not been exposed. Let's explore this with a formula. As usual, I let Y denote outcome and X denote treatment. Then we need a potential outcome. After all, we are considering counterfactual risks. Let YA be outcome when treatment takes value A in all units of the study population. So Y0 is the potential outcome in the absence of treatment. The attributable proportion describes the observed outcomes that would not have occurred if the population received a different treatment. To find it, we subtract from the observed probability of outcome the joint probability for observed and potential outcomes. We then divide the resulting difference by the observed probability. The result is the true proportion. Denominator includes numerator. Its value varies from 0 to 1. The attributable proportion in population is a classical counterfactual in epidemiology. But let's change our focus a bit. If interested in the proportion of outcomes among exposed that wouldn't occur if they were unexposed, we move to necessity. Necessity refers to expectations that absence of exposure prevents outcome, when exposure and the outcome occur together. The probability of necessity can be thought of as the proportion of exposed outcomes that would be avoided in the absence of exposure. That is, we look at exposure and outcome occurring together, and then we ask, to what extent eliminating the exposure would have prevented the outcome? We find the proportion of outcomes among exposed that would not occur if they weren't exposed. In clinical settings, physicians often advise patients to reduce their exposure to unhealthy habits, such as smoking. They expect to reduce health risks in current smokers. They rely on counterfactual reasoning that health conditions would not occur in smokers if they didn't smoke. Or consider patients eligible for bypass surgery who died after angioplasty and ask how many deaths could be avoided if they had surgery. That is, we want to know the proportion of angioplasty patients who would have survived if they had surgery. This proportion is what Pearl calls the probability of necessity. The probability that the absence of event X is 1 would prevent event Y is 1 if both X is 1 and Y is 1 occurred. This is a counterfactual situation, not the world as it is, but as it might be. To describe it, we simply condition all probabilities in the attributable proportion on the presence of exposure. This formula shows that instead of overall risk, we look at the risk observed in the exposed. Similarly, the joint probability for observed and potential outcomes is conditioned on the exposure presence. You have seen the formulas that determine the attributable proportion for population and for the exposed. They contain both observed and counterfactual quantities. We can estimate the observed risk as a sample mean, but counterfactuals always come with this lingering question: can we even identify them? After all, attributable proportions include a joint event that can never be observed. What does it mean that probabilities of counterfactuals are identifiable? Well, it means that we can express them in terms of the probabilities of observable quantities. Can we? Yes. The answer is yes. Probability of necessity is identifiable under some assumptions about the event-generating mechanism. One such assumption is monotonicity. Monotonicity requires that change in treatment X from 0 to 1 cannot, under any circumstance, cause the outcome Y to change from 1 to 0. In epidemiology, this assumption is known as no prevention. Simply put, no one can be helped by exposure to a risk factor. How can we use this assumption? First, we can state that if outcome is monotonic with respect to treatment, then the attributable proportion is identifiable whenever the mean potential outcome is identifiable in the exposed population. And then we can use a simple formula to find it. We take the difference between the observed risk and the counterfactual risk and divide it by the joint distribution of treatment and outcome. This formula is always true when marginal risk P0 is identifiable. We can find it directly from experiments or indirectly from observational studies by conditioning on pretreatment factors. For example, this marginal risk is always identifiable by conditioning on the parents of treatment variable. The backdoor criterion gives us other sets of conditioning variables. This is the most exciting moment in the entire course: the realization that we can calculate the probability of necessity through causal analysis. Let Y stand for outcome and X for treatment. Let Y0 be the potential outcome in the absence of treatment. Using this notation, let's rewrite the attributable proportion formula under the assumption of monotonicity. The first term on the right-hand side here is the excess risk ratio. In 80s and 90s, it went by the names attributable fraction, attributable rate percent, attributable fraction for the exposed, or even attributable proportion itself. Pearl argues that these names are misnomers. That's because the risk ratio is about statistical relationships. By itself, it cannot establish attribution, unless some causal assumptions are made. Monotonicity and non-confounding are two assumptions that give the excess risk ratio and the causality traits. And these assumptions are rarely made explicit in attribution statements. The second term is correction. We use it to account for possible confounding in the treatment outcome relationship. In other words, to account for the possibility that differences in outcomes between treatment groups reflect the influence of other factors, rather than treatment itself. Following Pearl, we adjust the excess risk ratio by the difference between the crude and adjusted treatment effects. Epidemiologists commonly use excess risk ratios to make causal claims. However, the claims are only valid under two assumptions: no confounding, and no prevention. We call no prevention sometimes monotonicity. When monotonicity doesn't hold, the excess risk ratio provides a lower limit for the probability of necessity. When confounding is present, the excess risk ratio must be adjusted. For instance, when bias is positive, the attributable proportion exceeds the excess risk ratio by the difference between crude and adjusted treatment effect. Here's the main point of this video. Probability of necessity is identifiable under no prevention and no confounding assumptions. You learned that these basic assumptions must hold before statistical measures can be used to establish causality. You learned that we adjust the excess risk ratio by the difference between the crude and adjusted treatment effect. You watched another episode of Causality with Boris.